have Noam, who is a disease ecologist at EcoHealth Alliance, who is our speaker tonight, and he's going to be talking about generalized additive models through the mgcv package. So I'll turn over the mic to him now.
I'm on. Okay. Am I on the other one?
Yes.
Okay. All right. Thank you. Thanks to Amazon, and thanks to Jared and his team for hosting this and continuing to hustle the New York R meetup all of these years. So I'm going to talk tonight about nonlinear modeling in R with generalized additive models and talk about the mgcv package. This is going to be a little different than the way I talk about this sometimes. I teach workshops sometimes on this, but what I want to do tonight is sort of give you a tour of capabilities and the kinds of things you can potentially do with GAMs, the types of data you can work with, the types of problems you can solve, because sometimes we tend to pick the package or the model that solves the problem that's immediately in front of us. Does the package work with data that's organized in the way that I'm working? Does it work with this type of output? Does it work with this type of data size? And we're not necessarily always able in sort of that immediate moment to ask, are we fitting the type of model that's appropriate for the overall system, the overall problem that we're dealing with? And a lot of the reason for that is we don't necessarily know deep in these packages what are the capabilities. And so I have an argument to make that generalized additive models are very good solutions for a lot of problems, but in order to actually use them, you have to know how to tie them to the different types of data and the different types of outputs and visualizations and challenges that you have. So let me just start with a little bit about myself. I'm a disease ecologist. My background's in modeling of infectious disease and modeling of wildlife and forest dynamics, and I work at an organization called EcoHealth Alliance, and we work at the intersection of conservation and human health. Most of our work has to do with how humans interact with organisms and how that relates to how diseases spill over from humans to wildlife and from wildlife into people. And it's a worldwide organization. We're headquartered here in New York, have about 100 people overall, and that ranges from wildlife vets to software engineers, data scientists in between. We have biologists, virologists, a really great wild interdisciplinary team trying to solve problems. And the reason this is relevant to the work we're doing is we really tend to work in trying to understand complex systems, not just to predict what's going to happen, although that's a big part of it, but trying to understand what are really complex interactions between wildlife population dynamics and cell viral interactions and human behaviors. And all of that requires a view on the models that we build that they represent these sort of complex nonlinear interactions in a way that we can understand. Before I jump into the models themselves, I want to give thanks to the beginning rather than the end so we don't miss it. There are three people who I've been working with on GAMs for a long time. Gavin Simpson, Eric Peterson, and David Miller are all statistical ecologists of various sorts, and we have taught these workshops together, and when we give talks on GAMs, we tend to exchange a lot of material with each other. So you'll be seeing their work and themselves as characters showing up a few times through the presentation. And we all owe a great deal to Simon Wood, who's a statistician at the University of Bristol, I believe. He is the author of the mgcv package and a great statistician and behind a lot of the important sort of applied GAM theory in recent years. So let's start off talking about why we might use a generalized additive model before we dive into the details of what they are. And the big reason is that we usually face this interpretability complexity trade-off in models that we fit. So we can fit models to data to do prediction that are linear models. They're relatively easy to understand. There's a straight line that represents the relationship between two variables that passes through a cloud. We're able to make a simple graph of that. We're able to make some predictions off of that. We're able to interpret it and explain it. But linear models may not represent our data well because our relationships may not be linear at all, and you may not get good predictions out of something like that. You move to the other end of the spectrum, you have all sorts of black box machine learning techniques. You have your neural networks, you might be doing random forests, you might be doing boosted regression trees. All of these things tend to be very good at prediction, but very difficult to interpret and very difficult to get understanding of what's going on in your system from fitting these models. So you might be able to do classification, but if you want to understand how one variable relates to your outcome, you're not necessarily going to do well, especially when you're looking globally. Sometimes you can look at sort of very local regions within your model and understand that, but to understand global relationships, they're very tough. GAMs provide a nice medium in this. You can fit relatively complex relationships, some complex interactions and nonlinearities in your system, but you can generally visualize these models. You can generally see what the relationship between different variables are and why it gets the outcome. So I sort of think of there being these three different components that you might think about as reasons to use a generalized additive model. One is you want to predict from a complex system. You have something that is complex and not easily understandable at sort of a linear level, and you want to be able to make predictions from it. But you also want to understand and make inferences about those relationships, about what variable is important and how they're moving. And then oftentimes what you actually want to do is you want to control for the complex relationships to ask for a very simple question. So if you're doing something like A/B testing, maybe all you really want to know is that, website version A is getting more clicks than website version B. But then you have to control for a lot of things that are more complex, like the seasonality or the demographics of the people who are approaching it, or sort of the time of day, or all sorts of number of things that aren't as simple as the simple A/B comparison you're trying to do. That said, GAMs are not bad at prediction at all. I don't want you to think that you are losing too much in this interpretability thing. So Kim Larson at Stitch Fix has this great post up comparing GAMs to a bunch of other models for the purpose of binary classification. I think the problem was here is from the insurance industry. There was a company that was sending out mailers, and they were trying to look at the characteristics of the people who got those mailers and how likely they were to become customers. And so there's a binary classification problem. There are 60-odd variables, maybe 10 to 20,000 data points they're working with. And she fit a variety of different models as predictors for this, from random forests, support vector machines, linear models, KNN-based models, and a bunch of different versions of GAMs. And GAMs perform about as well or better than most of these. You get relatively good predictive performance. And the predictive performance is that column of the validation area under the receiver operator curve, which is those 0.7 to 0.8 values of the accuracy of those models. So let me give you just a little bit of theory about what GAMs are and how they work. So GAMs, generalized additive models, each of those words means something. The generalized part has to do with what type of data and what type of outputs you're dealing with. When you have a straight linear model, you work with normal distributions of data, Gaussian data. A generalized linear model can handle many different types of outputs that are not normally distributed. So you can have binary data, zeros and ones, trues and falses. You can have count data when you're having counters of 0, 1s, 2s, and 3s, or things that are more exotic than that. The additive part means that there are multiple terms in the model, and they simply add together to get your prediction. The difference between a general linear model and a general additive model is that those individual terms are nonlinear. And then a model is a model that's not entirely facetious. Sometimes you have an algorithm that's predictive that doesn't have a model itself. It's just a representation of the data. But it does mean that underlying we have some representation of the process we're talking about. But the key difference is looking at linear versus nonlinear or additive terms. So if you have some data that is nonlinear like this, and this is from my colleague Gavin Simpson's work. He does paleoclimate, so we have a time in history on the bottom here, and the measure there is a proxy for temperature in one of the lakes he works in. So something is clearly changing over time here, and what we could do is we could fit a linear model to this, which would be a polynomial, which is the red line that goes down here. It wouldn't be a very good fit to the data. It wouldn't capture the complexity of this relationship in this time series. So another option is we could fit a polynomial. So we could fit a quadratic term, so x plus x squared, or something with x cubed, or on to higher and higher terms. And they each might capture more of the complexity of the data. But then first we have the problem of trying to decide what's the appropriate degree of polynomial to capture this. And then secondarily, even the polynomial type curves are limited in the types of curves they can represent. For pretty much any polynomial that's not explicitly modeling an underlying, say, quadratic relationship, you're going to get strange residuals and poor predictions, and especially poor extrapolation. So what you want is to model a relationship that can capture that data in a smooth way, get the main shapes, and not overfit the noise around it, which would be what this is, which is a smoother or a spline, which is sort of the essential building block of a generalized additive model. So how are these splines constructed? The way they work is they're built up of lots of little functions. So each spline is the sum of lots of little repeating functions that we have in the data, and each of those functions gets a coefficient, and then we sum those up linearly in order to get your output spline. So here, for fitting that data, on the left I have example of the splines before they get the coefficients, before they're fit to the curve, and then secondarily on the left-right, we have, once we put coefficients on each of those, they add up to that smoother. So each of these little functions is called a basis function, and the basis functions add together to get a spline. Now there are lots of different types of basis functions we'll go to, and one of the nice things about them is they can be tailored to the type of problem that you have, and they don't have to be one-dimensional. So basis functions can represent higher order relationships in 2 or 3 or more dimensions, so you can model a surface or the relationship between 2 variables in outcome with the sum of a bunch of 2-dimensional basis functions to create a 2-dimensional spline. So this is an example of that. On the bottom right, there's a fitted surface that we might use to model data, and it is made up of weighted sums of all of the other 3-dimensional surfaces of 2 variables that are there. So you multiply each of those relationships by the little coefficient by them, you get that thing on the bottom right, and that's how we assemble this complex relationship that lets us model a complex system. Now, these splines have to be the appropriate level of wiggliness, right? They have to fit our data but not our noise. And so the fundamental problem in fitting a GAM is optimizing that degree of wiggliness of your spline or your smoother. And so you have a trade-off to make in that. So there's a degree of fit, which usually is a measure of the likelihood of the model, which I have on the left of this term here. And then on the right, there's a measure of wiggliness, W, which is essentially just how much a function oscillates. And balancing the two is this smoothing parameter here, which we call lambda. And so when one is fitting a model, you're basically running an optimizer to pick the right lambda to trade off between fitting your data and avoiding fitting your noise. So dealing with lambda is sort of the core of what mgcv does, and you want to make sure you have it right, which, ooh, that's not what I want to do. Nope. Missed the big reveal. Where do we switch? All right. Let's just do this. All right, there we go. So if lambda is correct, you'll model a relationship well. So in these three graphs, we have a real process in blue and a fitted model in black with noisy data around it in the circles. So on the left, we're fitting our relationship well because we have picked a correct lambda. But if our lambda is too small, near 0, you're going to overfit data because you're going to have too many bases and too much wiggliness in your function. Or if your lambda is too large, you're going to have too simple a function to represent the complexity of your relationship. So really the core problem to solve is what is this smoothing parameter and how do we balance overfitting versus capturing the complexity in our relationship. And there's a lot to talk about how these smoothing models work, but we're going to skip that tonight because I want to talk about capabilities. So we're going to cross that out and remind you that this is what mgcv does for you and is sort of the core contribution to the package. And I can talk a great deal about it later on over beers or otherwise, but I want to move to how we actually fit these things in R on a practical basis. So let's get to a little bit of the syntax of how we build these models in R. So fitting a GAM in R works a lot like fitting a linear model or fitting a generalized linear model. If you fit a linear model in R, it's a function you call LM. You define a formula of your model. So your outcome y is a linear function of variables x1 and x2. And those x1 and x2 are in your data frame. You pass that function in your data. The difference with a generalized linear model is in addition to your formula and your data, you are giving a distribution family to say what type of data you're working with. So you might, instead of normal data, say we're working with binomial data or count data with a Poisson family or something like that. mgcv is similar. So if you load the mgcv library, you first define and you run the GAM function and you define a model formula. So the model formula is similar to a linear or a generalized linear model. You have an outcome, your tilde. You can have a linear component to that model, as we have an x1, or we wrap the variable in this S function, the smoother, which will produce this nonlinear relationship between x2 and the output. Once again, we pass the data frame of those inputs to the data. We can give the family. In this case, we're saying Gaussian, so a normalized output. And then finally, there's this component method equals REML, which stands for relative maximum likelihood. Method tells mgcv what method it should use to pick lambda, that smoothing parameter. Again, we could go a lot into it, but pretty much, unless you have very good reasons, you should use REML as the method. It's not the default, but the package author or all the theorists would say this is the right way to do it these days. The default is just there, essentially for backwards compatibility, which is this GVP method. If we dive into the formula for the GAM model itself a little bit, we see there's more components you can have. So the GAM formula first can have a linear term. If you want something linear in there, you can have it, which is just putting that x1 value up without anything wrapped around it. Then the smoother function, which you wrap your other variable in, starts with the variable itself, and then it has a number of other arguments. The BS argument is the basis. That tells you what type of spline or smoother you want to build, what types of functions to build it up from. The default is what's called a thin plate spline, which is a very good option for a lot of cases. You have a k value, which is the number of basis functions you're actually going to include. So you actually have a lot of leeway with k, because the smoothing parameter takes care of how complex your function is going to be. So k just has to be large enough to represent what might be the complexity in the model. The smoothing function will smooth it down if it's too much. So you just don't need it, you don't want it to be too low, because then you can't represent complex data. And you don't want it to be so high as to overload your machine computationally. But within that, the great thing about mgcv is it takes care of it for you. And then there's a bunch of other options which tend to be dependent on what type of basis you're using, and we'll get into those when you do those. So you fit a model, you can get an individual, you can get a spline, which is a relationship like this. But maybe you want to have a complex multidimensional interacting relationship between multiple variables, 2 or more. So there are a number of different ways you can do that. So you might have multiple splines that add up. So that's the first line here. Just outcome is the sum additively of spline of x1 and spline of x2. But you can make an interacting term, which is 2-dimensional, like that surface I showed you, of just saying, let's have the output be a function of the spline of x1 and x2 together. And that gives you a 2-dimensional relationship. That 2-dimensional relationship assumes that both x1 and x2 should be equally wiggly. So you have a surface that's equally wiggly in both dimensions. You can relax that as well with this alternate formulation called with TE, which is what's called a tensor spline, which does the same thing but uses 2 different lambdas. So x1 and x2 might make sense if you're looking at 2 dimensions in space, but if you're doing space and time, which are clearly operating on different scales, you might use something like a tensor. And one of the neat things is you can pull apart the relationship and have what is the part that is just x1, what is the part that is just x2, and what is the part of the interaction. Just like in a linear model, you might have 2 linear terms in interaction. And you do that by having a tensor of x1, a tensor of x2, and then a tensor interaction of the 2. And then you can manage those variables and those interactions independently. So what does this actually look like? So I tell you, these 2-dimensional GAMs are very good for representing things in space. So one example of that is this work by David Miller. David is a statistical ecologist who works in marine systems. Most of what he does has to do with finding and counting whales and dolphins. So this is data he's worked with in trying to model populations of dolphins in the Gulf. So we have a bunch of data from NOAA trawl surveys where they go out and watch for marine mammals. And so as they do that, each dot along this path that they they look out and observe for dolphins and see the number that they count. But we want to model that as a full 2D surface. So we create a GAM where the density of dolphins, d, is a spatial function, so an S of x and y being the coordinates on the map, okay, and also a function of depth. So now we have an additive model that says these are the 2 components that we think are important, location and depth, and figuring out where these dolphins are. We're going to give it the data of dolphin observations, and then we can make a prediction, which is this surface, which is brighter where we have a higher predicted density of the animals and darker where it's not. So that's this spatial approach is a really good way of using GAMs because that term S of x and y can really soak up a lot of the unobserved variation beyond your other variables that might be explanatory, like depth. That uses sort of the standard basis function. I showed you initially that the thin plate spline, that TP was the default. There are a lot of different basis functions for different types of things you would like to model. So if we're continuing to make models of spatial data, you're doing, you're mapping city travel. You're looking for where voters are, right? There are a number of specialized smooths for problems you might encounter. One of them are these soap film smooths. Maybe you're modeling a system where the topology is somewhat complex. So the example we might have here in my work is if you're looking at a lake and a lake is a complex shape, then you should have, what's here in the lake does not relate to here in the lake. Even though it's close sort of on an absolute basis, there's this peninsula blocking it off, okay? So if we just say BS equals SO and say we want a soap film smoother, it will understand that we have a shape we want to work with, and we pass in a list a simple polygon, and it will understand, model the spatial data within this polygon and don't cross the boundaries. So that solves one type of spatial problem. Another spatial problem that you might have is you're working at a very large scale. You're doing something global. And so it matters that things can go around the world one way or around the world the other way. And it matters the projection of data onto a sphere. It's not a simple x and y. So there's another spatial basis type for another type of smooth called a spline on a sphere. And all we have to do to get that is pass a basis of SOS, and then we can just pass latitude and longitude coordinates, model a system where we're looking at spatial variation along a sphere on Earth or any other planet you might be modeling. So those are good basis functions for space. There's also a whole series of ones that are good for time or combined systems. So I tend to use a lot what's called a Gaussian process smooth. Has anyone worked with Gaussian processes in other contexts? Very few. OK. So a Gaussian process is essentially a very good way of representing autocorrelated data. So a lot of times when you have time series, if you were to fit a normal spline or a linear model to something in time, you would have autocorrelation amongst your residuals. You wouldn't get good estimates of your errors. It wouldn't account for the fact that your observations aren't independent. Each one is reliant on the next. And that's essentially the type of variation that Gaussian processes capture. So in some of the work where I do, we are actually sampling bats for viruses against antibodies, and we follow a cohort over a period of time to see how diseases are cycling in these animals. And so we measure their blood for for whether they've been exposed to a disease, and we can see how the disease cycles in the population. We want to model that so we can predict in time how that'll work. So this is a graph of that. The dots are showing at individual points where we're sampling how prevalent antibodies against the virus are. We fit a spline in time, and I use that Gaussian process basis to create that spline, and that takes care of that time autocorrelation problem for us. If you're doing something in time, like if you have something with website clicks over time, sales over time, when customer acquisition happens, when different interactions happen, you probably have something that has to do with a seasonal component or a weekly component where things are always different on the weekend, or a monthly component because things vary over the course of the month and people act differently right before they've paid their bills and right after they've paid their bills. So you probably have something that cycles in time, and you often want to understand what's the cyclic component versus what's the long-term trend. And that's a natural fit for an additive model because those are two components you can add together that themselves are nonlinear. So for another version of this work, where we're looking at a series of viruses within our bat population, we wanted to know what the seasonal component was. Was there a season that was more prevalent? And how did that compare to the changes over a longer period of time? So for that, I fit a GAM that has that same Gaussian process, which helps take care of the autocorrelation and do the long-term work. And then add another smooth with a basis that's CC, which is what's called a cubic cycle spline. And then that type of spline, which is the ones represented in the graphs on the top, is flexible, but the beginning and the end is always the same. So it can represent a cyclic component like your weekly or monthly or seasonal or annual things. Then there are smooths that are not purely smooth. So this is something that David Miller had said when we were having a conversation about this, which is that ultimately what a smooth is basically assembling a relationship out of smaller parts and then penalizing its complexity some way to deal with noise. And in a broad sense, you can represent any type of relationship this way, which means they don't necessarily have to be sort of continuous splines. You can have discrete or other types of relationships represented in the same way smooths are, and that lets you fit a broader class of relationships as well. So the simplest version of these is discrete random effects. You might just have a bunch of different categories you want to model. So each, you can have some things like age classes, or maybe there's a difference between, how much people like a different color of a product, which are a different discrete category, and you want to model those different levels as part or as a whole of a GAM, and you can just do that as a random effect. This would be a random effect in your other generalized linear mixed models that you might fit with the LME4 package or the NLME package. But all it is essentially is that we have these smaller components that we penalize so that they don't differ too much from an overall component. And for a GAM, you just use the RE smoother to represent this and pass X as a factor so you can model discrete levels. And one of the neat things you can do is we had continuous interactions and we have these discrete levels. You can actually have interactions between a discrete level random effect and a continuous smooth. So let's say you have patient progression over time. There's some overall effect of, say, how someone's health or response or some other relationship is changing over time, and then there are differences between the individual patients for that as well. You could model that using what's called a factor smooth interaction. And there are two ways of specifying this in mgcv. There's sort of a shortcut, which is the factor smooth. So in the first line here, we model an output as a function of an x that's a continuous variable and an x that's a factor variable. So continuous might be time, the factor might be which patient, and the basis we use is factor smooth. And that's just a shortcut for a tensor smooth in which one basis is some sort of continuous version and one basis is this random effect. Now, one of the things you can do with this is you can pull out an overall effect and then look at how different groups or different individuals deviate from that. So this, once again, looking at our bat virus circulation work, we had a series of different bats measured when they were born and then how things progressed with them over time. And we were interested in how that overall effect worked in the wild and how we could predict it, but then how the different groups of bats actually varied from that. And so this case, we do an additive model where we have an overall effect and an interactive effect. So we have a GAM, we have an outcome. In this case, it's binomial, though I left that off the formula. I use one smooth to represent the central effect, so the continuous variable in time, using that Gaussian process. So we're using that, we're dealing with autocorrelation. And then we have another effect that's the interaction of that process, the factor of which group of animals we're looking at, and the basis is the combination of a Gaussian process and a random effect. And so you're able to separate those components out, and in the graph we have sort of the overall pattern of everything in these thick lines, but we can see the individual deviances and capture the variation there. One of the really interesting sort of spline-like things that's out there is something called Markov random fields. These are really good for modeling when you have spatial area data. So spatial area data is just things like countries and states and counties or land use or parcels where you have areas in space that are adjacent to each other, but themselves are discrete units. We don't have sort of continuous spatial variation. And they're kind of like random effects and kind of like smooths. And the idea of a Markov random field is that something in space that's a unit like that has its own value, but it probably correlated with the values of things adjacent to it, right? So you're not necessarily just saying, oh, this is its own value and it's probably some deviation from an overall mean, but something in county X is most likely to be correlated to county Y that is next to it. And so that still fits into this overall, here are the components and here's the penalization framework where we say it has its own component as its own effect. We penalize it to make it more like the thing is next to it. And we can just do that with a smooth whose basis is the Markov random field. And in this case, you pass a list, which is just a list of neighborhood. So that can just take a list of polygons or a list in which there's a vector which shows what are the neighbors of each individual component. So it actually works for anything you can represent as a network or a graph. So another field in which this works is when we do phylogenetics, looking at the relationships and ancestries of different species in our work. We can look at the neighbors as things that share a nearest ancestor, as organisms that are similar to each other, whereas ones that are sort of further along the tree are further away. This example here is county-level educational attainment. It comes from Gavin Simpson's blog, which I'll have the link for later, and it sort of shows how we have variation, but also spatial correlation amongst counties in terms of how many people attain a high school degree, and that's what's able to be modeled in this Markov random field way. Finally, there's something called an adaptive smooth. So most models I described have a single penalizing component, which gives you an overall wiggliness of your curve. But sometimes you have the challenge where the relationship is different along different parts of the range. So on the left, we have a traditional smooth. So we have a part of our relationship. The underlying real relationship is in red. The model is in black with the confidence intervals in gray. It's totally flat for some part and then gets wild later on. And the model has trouble capturing the fact that something is totally flat on one side and wiggly on the other, because it has a single sort of overall wiggliness defining it. So you can have the wiggliness itself change as a curve over time, and that can capture that kind of effect. Though this type of spline is just a little more data hungry because it has to fit these pieces piecewise and have enough information to do the penalization along the way. So you have a whole wide set of smooths, and the smooths capture different types of relationships. But you also have a whole bunch of different types of data and types of outcomes you might be modeling. So you might say, OK, something is going to be nonlinear related to y, but my outcome are ratings or count data or types or choose or false or things that are much more exotic. And those are things that are implemented in lots of packages throughout R. So your general linearized model will capture a certain set of distributions. Then you might have a package for a beta distribution because you're modeling probabilities. Or you have a special package for the type of sensor data that you're looking at as well. One of the neat things about mgcv is just the sheer number of probability distribution outcomes that have been built into the package. So you can capture a lot of those different types of things without wandering off for something specialized to the problem. So one example of that is dealing with data that has a lot of outliers in it. Maybe the data you have has very fat tails. It doesn't fit with a normal distribution because you have a lot of extreme values in it. So you would want to fit a model in which your outcome distribution is fat-tailed. If you fit a normal distribution, it wouldn't capture it right. The GAM mgcv includes a student's t distribution. And the student's t distribution can adjust the fatness of the tails from being like a normal distribution to being much broader. And if you fit data that has a lot of outliers, like this example here, if you would use a normal distribution on the left, those outliers would really mess with the relationship. The red GAM wouldn't capture what's the black overall true relationship with all those outliers. But if you use a student's t distribution with those fat tails, you can capture it much better. You might have count data. There's standard count. There's a bunch of standard distributions you might use for count data that you use in generalized linear models. There's a Poisson distribution, which is for count data that's sort of evenly distributed throughout the individuals you're looking at. If you have over-dispersed data, you might use the negative binomial distribution, which is also common in general linear models. But there's a series of others that could be more exotic. So for instance, mgcv has implemented the Tweedy distribution, which is very good when you are looking at counting things that are clustered in groups. And so you're missing those groups sometimes, and you're hitting those groups sometimes. And that's actually exactly what we use in this dolphin data where we're modeling in space. So dolphins aren't just like evenly distributed through the sea because they're social and they come together in pods. And when you go out and you watch for them, you're not going to sort of get them evenly, you're going to run into groups of them and get big numbers and small numbers, and that can't be represented with a Poisson or even a negative binomial very well. But a Tweedy distribution captures that type of problem very well. Maybe you have an outcome that's not a measured number, but you have an ordered categorical data. So ordered categorical data could be ratings. You have something on your website, people are rating 1, 2, 3, 4 stars. You have survey data in which people are rating things on a scale of 1 to 5. So it's numerical, but, and there's an order to it, but things aren't necessarily continuous in that range. They're not necessarily evenly spaced. GAMS can handle that very well. There's a setup for ordered categorical data where essentially you fit a spline or a smooth, and the GAM fits just thresholds along that to determine where something transitions from one group to another. So then capture the fact that people are really normal when they're going to 1 to 4, but really hesitant to rate a 5. So you can't just think of things as linear. You know it's something more complex that causes them to jump from level to level. So this is an example in which we're looking at what makes it more or less likely that something is categorized in these different conservation categories by the International Conservation Union in terms of different species. And so we look at how animal size affects that. And as size changes, it hits the relationship on average hits thresholds that move up between these different categories. And all you have to do to do that is have your outcome be an ordered factor in R and give the family as OCAT to capture this. There's a lot more in this. You might be categorizing, you might have non-ordered categories that might be exclusive or not. So you're predicting tags on a document or something like that. Or you might have something where the outcomes are multiple. You're trying to predict height and weight. You know they're correlated, or they're both outcomes of the same process. Both of those things that there are families for, you can do the former as a multinomial, the latter as a multivariate normal. Both of these are in mgcv. You just pass a list of formulas that can be the same formulas for the outcomes or different formulas. So you can say, well, we have a common process, but the variables are a little different for the different type of outcomes we're looking at. Or that the same things are predicting the same types of outcomes. So in the first one is the same. We say variable x1 and x2 both help us determine the category, and we have two different categories because we say k equals 2 in our family. But in the bottom case, we might say, well, we have two different variables that are potential outputs. The first one is predicted by x1 and x2. The second one is predicted by x1 and x3. So they share some information, but not all. I probably covered about 2/3 of what's there, but I'm not going to go through all of the other distributions. But the big message I want to say is that if you're using a GAM, it very likely can solve a problem if you have a particular distribution of the outcome of data. mgcv has outcomes for survival data. It has, if you have to model the variation and not just the mean of your data, if there's sensor data, there's and then there's a series of others. And Simon keeps adding more of these as we go. So you rarely have to leave the world of this package to get the outcome you want. There's beta, proportional stuff, and a bunch of others. So that covers, on one hand, the types of relationships in our splines. It handles the types of outcomes. But then there's a bunch of other problems you might have that you're trying to solve, and there's that are your main based on your main predictive goals, and mgcv is able to solve a number of these. So one problem is variable selection. You have a model, you're not interested in just prediction, you want to select what are the most important variables there, so you can discard the rest, so you can have something parsimonious, something that is easier to explain, something that is easier to collect the data for, something that will run quickly. So mgcv has this great argument, select equals true, to add to the end of your model to do variable selection. And what select equals true will do is add, in addition to a penalty on how wiggly the relationship should be. It'll add a penalty on its overall slope as well, which is the same as doing something like ridge regression or a lasso, which essentially penalizes too much of influence of the relationship unless there's enough data to support it. And so if I fit a model that has 6 smooths for 6 different variables, but 3 of them are spurious, but it will just eliminate those variables altogether and leave them as nothing but 0 coefficients on the model. So we have the individual splines that are fit for each of these up here. The 3 on the top, x1, x2, x3, actually mean something. The ones on the bottom are just completely factored out. And so you can run your model and say, we don't have to use these at all. It doesn't, they're not significant, they're not predictive, they're penalized out. GAMs can be relatively computationally intensive, but it's something that Simon has actually worked a lot on, which is creating this alternative function called BAM within GAM, which is sort of like the big data version of GAM. It basically, you're able to do a lot of what you're able to do with GAM already, but it uses a set of approximations and is able to do sort of a more memory efficient and parallelizable approach. So you can scale from what you might have in a regular GAM with thousands of data points to sort of the tens and hundreds of thousands, or lots more interactions with something called BAM. So I just have 2 examples here of running GAM, and BAM is about 10 times faster on this sort of example of 10,000 data points or so. But the bigger thing about it is it's much more memory efficient. So you'll probably, when you have a big model with lots of different interactions, you can easily overload the memory of a machine. BAM is able to do things piecewise in such a way to avoid that, so you can handle much larger problems. And it has almost everything in it that GAM can do. Some of the weirder output distributions it's not quite capable of handling yet, but it has more every time, and probably eventually will just replace the basic GAM function. Maybe what I'm describing doesn't even adequately capture the relationships that you've had. You have something that has complex, nested, hierarchical effects, and you're someone who uses multi-level nested models like you might have in NLME or LME4. Now there's these extended components, the generalized additive mixed model and the updated version of generalized additive mixed model 4, which is a separate package, but a partner to mgcv, and it basically combines the LME4 package with mgcv and lets you have these complex random effects in a model. And so this bold part, random effects, lets you have a sort of a nested hierarchical structure for your slopes and your intercepts, and combine that with the smooth functions in a GAM. Or maybe you're a Bayesian, you're an iconoclast and a bit of a masochist, and you want to make sure that you have informative priors and you are modeling something that has full distributions of the posteriors and be able to draw from that. And that's something that is they're rapidly developing more options for it too. Simon developed this function called JAGAM, which will generate JAGS code. JAGS is a Bayesian sampler, just another Gibbs sampler. You run JAGAM on your GAM, and it just generates the code you can run in that other program. If you use Stan, if you're a fan of Andrew Gelman, as a lot of us are here, and his work, the Stan team in the RStanArm package has developed a function that basically clones your mgcv model based on what's in GAM4, and it runs it in Stan and it returns it. And so I sort of have an example here of modeling time series data with that, where you can draw from the posterior of that Bayesian model and generate lots of different posterior splines. And then if you're like really at the experimental cutting edge of Bayesian modeling, there's this new package called Greta, which is Bayesian modeling built on top of TensorFlow. It's just starting out. David Miller has implemented an experimental thing where we can take the output of JAGAM, turn it into Greta, and so then you can run your Bayesian models in TensorFlow and use GPUs and get all of this associated and speed up and connect with other tools associated there. So I've given you a whole lot in this in terms of spline types, output types, other features. This was certainly not an introduction of a how-to so much as sort of this merry-go-round of possibilities of how you can model things with GAM. So let me just give you a little bit of resources you might go to do more. First of all is within the mgcv package itself. Simon has a tendency to write half of a chapter of his book and make it a help file and stick it in the package before he updates the version of his book. So if you go into the help of mgcv, you'll see beyond these very helpful functions, function documentation, there's a bunch of things like these smooth terms, missing data, GAM selection, which are like short essays on how to deal with certain problems. So they're not vignettes, which is where you would expect to see that in the package. They're help files. So dig into that when you're doing that. He also has a book that's very good. It's relatively mathematical, but it starts at a very basic level. So it's a very good stepped thing from linear models to generalized linear models to generalized additive models. So it's sort of heavy in math notation, but it presumes very little from the beginning. So that's a great resource. Secondarily, Gavin Simpson has this spectacular blog of his from the bottom of the heap. About 60% when he blogs about is experimenting with GAM stuff. And so he'll always post code and data. He'll try things out. He has a recent thing on using Markov random fields and how to do it. That's where that map of educational attainment come from. He will be trying things out constantly. We're constantly debating about approaches to that. He's fantastic. He's also, I had to do this because he's the kind of guy that you can goad into doing your work for you if you do something correctly. So someone posted this on Stack Overflow, this spatial thing, and he wrote down here, had something, I'd like to do all of this, but it's kind of hopelessly complex, which is just like a way of goading him to putting together a really complex model, assembling the code for the whole thing, giving you a whole, his model was fitting. He has one set of outputs as an example of these relationships. He has another, a different alternative formulation, predicting across the whole data set. He made this animation, I think, this is while the Markov random fields were fitting, I think. And so, I just need to give this guy a shout out because how supportive he is and how useful he is for asking questions about that. I call this trolling-driven data science with Gavin. Ask if a GAM can do, say the GAM probably can't do it, and he'll show you a way that can. That said, Gavin, David, Eric, and I, we've taught a workshop every year for the Ecological Society of America, which probably most of you are not going to, but we put all of those course materials online. They're on my GitHub account. We have slides which are very different than the slides I showed here. They show a lot more code, a lot more outputs, a lot more how-tos, as well as a series of exercises that are both created by us, by our data, and stuff drawn from Simon Wood's book. So that'll be available. Finally, hopefully sometime in spring, there will be a data camp course that I'm currently late on getting some stuff to put together for. But sometime in the spring or so, we will have a data camp course on essentially how to fit these models, how to check these models, how to visualize these models, and how to predict for them. So hopefully between those things and between my sales pitch about the wonderland of different approaches that mgcv gives you, you might be able to do something with GAMs that's useful for you. And that's it. Thank you very much. All right. I don't know how late I went. So questions. All right. All right. Great. Yeah, so I didn't go to. GAMs have a predict function S3 method, just like you have for linear models and generalized linear models. It's like the others. It's predict.gam. It'll give you the predictions for your model as it is. You go to the help for predict for.gam. There's a lot of different options because you can say predict for the individual smooths. You can predict with or without the intercepts. You can create sort of, you can export using the predict function a matrix, which lets you do all of the calculations with a simple sort of linear function. So you can export that to a different language or a different framework. So you can use a GAM that you fit in R to run something in JavaScript because you have the prediction matrix from it. But it's this sort of same standard predict framework. A lot of the other standard frameworks wrap it. So the Broom package, which does tidying of coefficients and predictions, its tidy and augment functions all work on GAM. There's a GAM wrapper in the Caret package for prediction, so you can put a GAM model into Caret and compare it against other predictive models you might build. And has most of the standard infrastructure that you see around predictive and inference models in R. Yes?
So assuming the method is implemented in GAM, is there any reason to use GAM over GAM, even if you don't have big-ish data?
I'm not sure about. So I mean, it's an approximation. Like my guess is that for most cases, those approximations are not going to make a difference if you have noisy data. So it discretizes some of your continuous data to simplify some of the calculations, essentially. And then again, you might have some of the, basically up until the last version of mgcv, a whole lot of the distributions were not available. Now, a lot more of them are. So it's becoming a smaller and smaller set of reasons to avoid it.
In your examples, you showed like the number of independent variables are like minimum like 2 or 3. Let's say like if I have like 15 to 20, like how do I come up with the combination of these variables? Like since there is like different combination we can go up with, and how we can say like this is the optimal way of coming up with the different set of variables. We can also include polynomial features also included. So how we come up with that particular line?
Right. So I mean, and so this is a little bit about where sort of the philosophy of the GLM or the GAM can butt up against something like the random forest, because you have to make the decision yourself, right, as to what you want to represent and what degree of complexity you want to represent. In my experience, actually having interaction terms of more than 3 starts to get out of hand, because the number of terms in the model is increasing exponentially as you do that, and so when you start having a smooth that's smooth of A, B, C, D, E, and F, both the optimizers don't do particularly well in finding the right coefficients, and then from my perspective, more importantly, that is at least as difficult to interpret as anything else. I mean, once you start having that degree of interactions, you're very unlikely to be able to directly interpret what's happening. You can't visualize beyond sort of the 3D spline, right? In which case, it might make more sense to do something like a random forest for that degree of combination. That said, we have plenty of GAMs that have 40 variables in them. They're just not necessarily interacting variables. So the interactions tend to be 2 or 3 different components that we're interested in that and we think are important. And then everything else is additive. So individual, not more linear terms, but more 1 or 2 dimensional splines. And that's where it really gets to what your particular system is that you're modeling and what you're interested in and what's optimal doing 1 or 2 or 3.
How big a size of a data set I've experimented with that.
Yeah.
You have to, let's say, RCS, that was slow, but it's manageable, give a result. I tried this with millions of rows. It seems like, well, maybe I did
Yeah, no, I mean, so, GAM, like the base GAM, is something that's tends to work in the thousands of tens of thousands. BAM is something that, I mean, it depends on what you're, with BAM you can start using, like you have multiple threads and you can do more things and there's a lot more variation. But I haven't worked with BAM with more than hundreds of thousands of rows. That said, so one of the things is that there's this rule of, I don't know if it's proven, it's more than a rule of thumb, but so the complexity of a spline sort of increases at, it's a rule somewhere, a 1/5 power of the number of of the amount of data that you have. Okay, so the more data you have, at a certain point has very little influence on the complexity of the spline that you fit, essentially. So there's sort of a plateau of the amount of data you need. Probably you're not going to get a big difference between a model that randomly subsets, 100,000 out of your 10 million points than uses all 10 million points.
It's a sparse, little bit relatively sparse, like a low imbalance problem. So that's why the data size.
Yeah, so one thing, I mean, and BAM does it a little better and GAM doesn't do it great, is sort of computationally, it doesn't do a whole lot taking advantage of the sparsity, right? So like the matrices that make up these smooths are sparse matrices, but very little in GAM actually takes advantage of that computationally, and that's the reason that you have these challenges. BAM improves on it, but in a partial sort of piecewise way as opposed to like moving to an entire sparse structure. Well, no. So what happens is within the GAM, we don't. GAM is with this select equals true argument within GAM. When we add this, it's doing something that is almost exactly equivalent to a lasso in and of itself, right? So the central thing that GAM is doing is it's penalizing the overall wiggliness of these functions. Your lasso actually penalizes the overall slope, right? So what select equals true is it says penalize both. Add one penalty for wiggliness and one penalty for slope. And so you're essentially getting the lasso effect here by adding select equals true. And so you don't have to do it, you're not doing a separate model here by doing that. And it'll also do that if you have linear terms. If some things are smooths and some things are just individual terms, you can have that select penalize those linear terms as well.
All right, folks, we'll take 3 more questions. I saw this hand. Gentleman over here.
We'll talk more.
So we can do these 3 questions, but we're going to go to the bar afterwards, and you guys can ask as many questions as you'd like.
I'll be there.
I have a question about the ordered categories.
Yeah.
Because I've done things like proportional odds and things like that. Is it still a situation where one is the reference?
Yes.
And does the reference stay the same all the time with the basis function?
Yeah, it does, because you have an ordered category. So just simply, the first one here is your reference, right? And then you have the threshold that switched and the thresholds that switch. So you're estimating for 4 categories, 3 thresholds, in addition to the smooth itself, right? And so you have like one of them is the base, and then what is the change going by this threshold and this threshold. But you do keep that reference category, much like when you have a fixed effect model. One thing is the intercept, and the rest are the fixed effects.
What's the advantage of doing this type of versus doing a proportional odds, where you just
It's very, this is very similar to something like a proportional odds model, but a proportional odds model is still linear. So what you might say that like the things that are affecting this outcome, right, along this continuous scale are not constant, because it makes a big difference as you move between the lion and the elephant size relative to moving between the cat and the lion size. And so it's the nonlinearity that's the point, and you can have that nonlinearity in as many terms as you want. Two more.
I was wondering if this thing is tested rigorously against synthetic data where we know the ground truths.
I mean, the overall package, so, I mean, mgcv has been in R's core for about 10 years now. Simon as a statistician does a great deal of rigor testing, both sort of like theoretically and empirically. So things like, you look at the, things like the select equal, like the selection stuff. He has a series of papers empirically on how well that penalization works versus other sort of like approaches like doing AIC comparison against all of the different models with all the different types of variables and how their performance is. In terms of the, like rigor of the code, there's definitely a pretty good testing coverage of it. He's relatively old school. mgcv is not on GitHub. It doesn't use continuous integration as far as I know. The most recent version always exists only on his computer until it's released through RForge and then RCran. I think it's as reliable as base R. He's an R core member. His statistical work is very good. These aren't particularly, this field is not a particularly exotic set of models. Ultimately, it goes down to these are linear combinations. It's not like some of the machine learning work is like purely empirical, right? Like we don't know why some of the machine learning neural network stuff works. So it's much more important that you have that type of rigor. But then ultimately what you have to do is you have to test your models when you fit them and look at the outputs and look at how they're working on your test data and your validating holdout. You certainly can get into cases where the optimizers fail, right? Like if you have too many coefficients, if you set your k values too high, you can have something hit some local minima that's not where the model should be. Usually the diagnostics will tell you that, but it's a thing you have to check.
All right, folks, this will be the last question, but again, we're going to go to the bar afterwards, and myself, Kaz, over here, all the way to the left, will be leading charge, and we'll actually have Matt do the charge when he's done asking questions.
Great, thanks, Joe. My question was about the select function within GAM. I was wondering if you could run it without actually running the whole GAM model on the whole data, so you can use it to filter out your variables before fitting the model if you had a really big data set. Does that sound practical, or would you use a different method to do that? Or would you just take a random sample of your data?
That would, no, the select, it wouldn't work that way. So what happens, so like the central machinery of what's happening is GAM is iterating, trying to find this correct smoothing value, this penalty, right? So it's doing that. It's measuring the likelihood of the model at a given smoothing penalty. It's adjusting coefficients and the smoothing penalty to get it right. The select equals true just adds more to that machinery by saying we're going to have another penalty, not just on how wiggly the functions are, but on how steep their slopes are. And so using the select equals true is pretty integral, like has to happen while the model is being fit, essentially. So if you're trying to eliminate potential variables you might fit, that would be probably the place where you want to do something diagnostic early on and like do your pairs plots to look at relationships essentially, see which ones have no correlations. One thing that is in the packages is a thing called concurvity, which is basically a nonlinear measure similar to collinearity, and that's one thing you might do is like looking at subsets of variables of how concurvacious they are to see if like they have some degree of relationship that you're interested in fitting and exploring more. It's also an important thing for checking your models, because just like collinearity, concurvity can screw up your estimations and your confidence intervals in